So, welcome to everybody. I'm Alessandra Lanotte. I'm chairing this second day of this virtual conference, Turbulence, Problems at the Interface of Mathematics and Physics, which is virtually hosted at ICTS. So the first speaker of today is Jayanta Bhattacharjee. But before letting him speak, let me tell you that so the talk duration is 45 minutes, and then we have 15 minutes questions. Please ask your questions in the chat of Zoom. And then an announcement. After the second speaker of today, so after Martin Heyer, we will have a discussion session chaired by Khanin. And this will be unrecorded and very informal. So if you want to join, please at the end of the second talk. So now let me give the speech to Jayanta Bhattacharjee.
Yeah. So what I'm going to talk about is turbulence spectrum, and we'll be sort of going we are going to talk about a sort of two halves. One where I'll talk about homogeneous turbulence, about things which are very well known, but sort of trying to give a slightly different twist, which may be somewhat all right, nice in some ways. And the other would be not turbulence in a stratified fluid, which can be a little more sort of less looked at field, and maybe something interesting there is something interesting there. So anyway, we get started with what everybody knows, that in this all the complex structure of the turbulent flow, there is something which is universal and somewhat easier than others to put your hand on. And what this is what Kolmogorov found 80 years ago, the amount of energy, kinetic energy stored in a small wave number range. And so the total kinetic energy, K, written as a sum over integral over the wave numbers, the E of K, which is the energy spectrum by definition. Okay, so so the point is that this Kolmogorov spectrum, K5/3, the epsilon, is the energy transfer rate from one K to the next. And that is supposed to be a constant independent of K. And that is what one calls, let's say, in this context, a mean field theory. And this universality is restricted over a set of wave numbers, which seems to be quite large, because if one does numerical work or experiments, you see this K to the power 5/3 over several decades. It is obviously not an exact answer. There should be small corrections, but in this particular correlator, that is low. As for the fact that the epsilon is a constant and there are fluctuations and multiscaling, you will be hearing a lot about that from Rahul. So we can go back. So here is what this once again, I mean, this is something funny here, which is which I don't understand, that this is on a timer some kind. Yes, of its own accord seems to be changing its so so question is, what is the universal range where this one sees this? So you consider the universal range is determined by the energy equation, and the energy equation, as you can see, is the left-hand side, the U square is the kinetic energy per unit volume, the total kinetic energy. It has a rate of change, which is a dissipative part, which has a derivative and therefore operates at low scales. And then there is a part which is a stirring force, the F of alpha. This is an incompressible fluid, and therefore that leads to this pretty easy equation over here. And the right hand side has a dissipation and a forcing in, and therefore you fix the scales that there is something going on at short wavelengths, short wave vectors. There is something which is going on at large wave vectors, and therefore obviously those places can't be universal. It has to depend on how you are injecting energy or withdrawing energy, but the universality has to be in the region where you are away from the injecting and the dissipative range. So the stochastic model, which came into being, was in 1979, De Dominicis and Martin, and the external force that we talked about, which was injecting energy into the system, was taken to have the correlation function was given by this correlator over here. So a delta function in wave vector and frequency, and falls off as k to the power d minus 4 plus 1. So y is a number which one could play around with. So the point with De Dominicis and Martin in 1979 was that they wanted to use what was very popular in those days was renormalization group for dynamics, critical phenomena, critical dynamics was popular. And so this was an attempt at making the renormalization group work. There was a problem, because at the Kolmogorov spectrum, which you saw a few minutes ago, was obtained at y equal to 4, where there were a large number of marginal operators. And what was also funny was there was some kind of a different kind of divergence at y equal to 3. So, all right. So now the question of scales, the renormalization group, which was in the mind of these authors, was something which works in depending on who is using it. If it's a condensed matter person using it, it works in the long wavelength limit. If it's a high energy physicist working, it works in the high energy limit. So low energy, high energy, and in between, what turns out, as we said, this is somewhere in between, and therefore the question of renormalization group giving you the right answer for Kolmogorov was a bit suspect. It was a nice starting out. At least the model is, as we will say, is something which one can fiddle with in very many ways. And what I would like to talk about for that model is that I can use age-old self-consistent perturbation theory and see how it can make sense. So what we want to do is talk about this in Fourier space, which is the convenient thing. And this is Navier-Stokes written down in Fourier space, the bilinear coupling, which you see is the nonlinearity and the cause of all the difficulties. The M is the coupling constant coming from the derivative that was there. And so, well, what are we going to do? It is this Y, which, as I said, that what De Dominicis and Martin introduced for setting up the renormalization group argument. We will claim that this parameter Y is actually a very useful tool for just perturbative evaluation of loop integrals. So that is the point that I want to make, that the stochastic forcing as written down by de Dominicis and Martin is very useful because if diagrammatic perturbation theory is a tool which one can use or wants to use, it orders the diagrammatic perturbation theory. So, all right, so what are the quantities which one needs to focus on? There is the rate of the important issue which arose in the Kolmogorov expression was the rate of energy transfer across at a wave number k. So if you imagine the momentum space and the sphere of radius k, so it is the energy contained, what is the rate at which the energy contained in that sphere is changing, and so that is the quantity that one needs to compute. So that's certainly one. That's a physical quantity in the sense that it appears in the Kolmogorov picture, and so it is something which we need to pay heed to. What's the other? The other is in a way also related to that, in the sense that it is related to this transfer. It is old Heisenberg Chandrasekhar business of eddy viscosity, which we'll see is a quantity which just automatically arises in a diagrammatic business, whether what one calls it, it was called eddy viscosity, but all that it is a renormalized quantity. So the energy in the range from 0 to k. So that's what this expression is, integral from 0 to k and the velocity squared. So, all right, what I want is...
I want to ask a question before you go.
Yeah, sure.
I didn't quite understand. Can you go back to the previous slide, please?
Sure.
So you say that you want to measure the rate at which the energy is transferring from one case field to another case field. Now, this, of course, is a fluctuating quantity. It sometimes goes out, sometimes comes in, and it's a fluctuating object that is changing in time rather rapidly. So maybe what you mean is that you want to compute the mean energy flux from one case field to the other, but that is simply in stationary conditions is determined by the rate of energy input on the large scale. So I'm not quite sure what you want to compute.
Oh, it is the average value. So it is the average energy content, as this over here makes clear, that it is the average energy contained in the sphere of radius k. And you are asking the question, what is the rate of whatever is flowing out of that sphere? What is the amount of energy per unit time flowing out of wave numbers less than k to wave numbers greater than k?
But this is a quantity that fluctuates strongly in time.
Yeah,
sometimes positive, sometimes negative.
Yeah, but that's where the fluctuation in time, this time average, it is the mean field picture is that these averages, these fluctuations are getting ignored.
So you want the average?
That is what.
So you want the average flux?
Tamar, can we discuss this?
Yeah. I just don't understand. So if I don't understand in slide 2, I will lose everything. So
just a second. Are you looking at the first line over here now? The rate of change. Yeah. No. Are you? Do you get the E of k, which is the integral over the energy content between 0 and k? I mean, which is the total energy by definition, the total average energy between 0 and k.
The total average energy, I have no problem. The total average, the average flux, I also don't have a problem, but that's a triviality because it's determined by the rate of pumping. And so I'm not sure what is you put a goal to what the theory should compute. What is this goal? I didn't understand.
The goal is to compute what is the amount of energy flowing from less than K, a particular, I focus on a particular K.
As a function of time?
Pardon?
As a function of time?
No, not as a function of time. It's a stationary situation where it is.
Yeah, but then there's nothing to compute. It's the average rate that you pump the energy into the system. The energy doesn't disappear, doesn't get created.
Yeah,
So,
no, but
okay.
It is the fact that the transfer is what I'm driving at is the fact that it is independent, the transfer rate is independent of K, while it is a question of what is being put in at per unit time is certainly what is being dissipated per unit time. The point over here is that if I want to calculate, the Kolmogorov picture says that it's a type transfer across every wave number. So K, if I look at the energy crossing from below K to above K per unit time has to be independent of K. So I'm calculating the transfer rate because of the nonlinear interactions and asking that it be independent of K. Yeah, I mean,
please go on. Please go on.
So it is E of K, the capital E of K is the amount of energy contained in the region between 0 and K, and that is changing because there is a flux over there. So, and every amount of flow per unit time from the K sphere to outside from less than K to greater than K, and that would be the time derivative, which would have to be a constant. So formally, the time derivative is what one has written down over here in first line, and then you are in. So the rate of change, that is this quantity over here, where part of it is the dissipative thing, which is being lost, which one is not interested in, and the other, the T of K, is the part which is just the Kolmogorov type transfer from one K to the K plus dk. So from below K to above K per unit time, T of K is the transfer term. That is, the viscous transfer is the part which is the second term over here, eta times this quantity, which is a negative quantity and left to itself would have damped things out. There is the forcing part, which I have not written down because simply because that is not something we would be talking about at all. So this is why I have this, is that if you want to look at this transfer term, the point with the eddy viscosity is that in analogy with the viscous term that you have over here, then you are going to write the transfer term as a coefficient eddy viscosity times exactly the integral which you see in the standard viscosity thing, which is why I have it up there, that the standard viscosity dissipation is P square EP, where E is the spectrum, times the viscosity of the fluid, whereas this transfer term, which I want to write in a form which looks like the standard viscous dissipation, and write it as this eta sub E times the energy spectrum. So just as the rate of energy transfer is the integral of P square EP dP, and with the extra P square is the P square which you would have associated with the del square, and you are writing the transfer term in a similar manner with the coefficient being what is this eddy viscosity which people talked about earlier. So that's the two players in this are the eta epsilon eta E, which is the eddy viscosity, and the transfer rate, which is this integral T of Tk. So you write the dynamics as the usual Navier-Stokes dynamics, and the transfer rate can be calculated, where the transfer rate, which is a 3-point correlation of the two velocities coming from the v dot and the third velocity coming from the rate of energy transfer. So the nonlinear terms providing your two velocity factors and the energy expression giving you the other. So the transfer is a 3-point factor, and the viscosity is a question of dressing the eta k square. So this term, the nonlinear term over here, dresses the eta. The dressing of the eta is the eta effective viscosity, which is the eddy viscosity as the literature gives us. And the correlation function is related to the energy transfer, energy spectrum. The transfer rate is related to the self-energy and correlation function. And for Kolmogorov, the epsilon k is the T of k, which is the transfer rate, and is independent of k. So that is what one wants to do, that you just set up a diagrammatic perturbation theory where you use perturbation theory to the diagrammatics to effectively dress the eta. So calculate the sigma k omega and write it as the zero frequency part of sigma k omega is the eta effective or eta eddy times k square. You arrange the perturbation theory by self-consistent loops. So there is no small parameter over there. And this is why, this is where this parameter y comes in, the external stirring comes in, because it orders the perturbation theory. So the way it goes is that you look at the one loop contribution. So you look at the one loop contribution, and if you look at this, if you look at the integral has a pole at y equal to 0. The sigma k omega over here is the is the one loop contribution. And if you put in the g's and the c's at the 0th order, you would find that there is a pole at y equal to 0. The zero frequency cell, and so, all right. So that is at one loop, the integral looks like, say, if I write out this right-hand side calculated, it would be 1 over y with a coefficient plus something of order unity plus something of order y, and then y squared, and so on. The correlator has this structure that it is G times the zero frequency self-energy. So if I use a self-consistent, say that it is like scaling holes and there is a k to the power z, then self-consistency of this would ensure that z is equal to 2 minus y over 3, y by 3. The integral has an ultraviolet pole at y equal to 0. So, but one needs amplitudes as well. So you set the frequency scale by this gamma 0. The correlator is the C of k omega, which scales as with the form that it is GF times FG. It has a form which looks like what you have over here, C0 divided by k to the power d minus 4. The ratio gamma 0 square over C0 is the ratio of two integrals. The integral for the energy transfer from where I'm calculating the C does not starts at order unity, whereas for the sigma starts at order 1 over y. So this quantity gamma 0 square over C0 turns out to be a over y plus order 1, and so on. The two loop if I now look at the two loop, it carries an extra factor of, so the 2 loop also has a 1 over y divergence, it has a pole at 1 over y. So does the 3 loop. Every loop integral has a 1 over y divergence at y equal as y tends to 0. That comes from the region where the external momentum is very small and the internal momentums are big, and that drives the divergence at y equal to 0. Each loop has a similar divergence. They start with a 1 over y. But now if I go to the second loop, I would be picking up an extra factor of C0 over gamma 0 square. So C0 over gamma 0 square is the extra factor which ensures that the second loop starts at 1. And if I go to the third loop, I pick up actually 3 factors of C0 over 2 factors of C0 over gamma 0 square and extra factors, and that ensures that I start at y square. So all the loops are actually demarcated by this y. The 1 loop starts at order 1 over y, the 2 loop starts at order 1, and so on. This drives the loop ordering in y. There is another issue with this, which is the question of infrared problem, that when p becomes small, there is a divergence in this integral over here. That divergence comes from if I focus on the part of the integral where k is big and p is small, the small p part, but then this is not real in the sense that this comes from the assuming a Lorentzian structure of for the frequency integration. If you see that there is going to be, if I look at the sigma, the self energy, it has to have a k as well as a omega dependence, and the sigma, where the self energy diverges at small k. So the correlator at low wave number gets screened by the frequency of the response function. So this divergence, which exists and often is called the cause of sweeping, which is not really there, and that is why the k to the power minus 5/3 is never really violated in any that strongly in any numerical work or experimental work. So that is the question of how a self-consistent perturbation theory can give a finite answer in principle. The calculation, so in some sense, it is if you work hard enough, you can get an answer where to several orders. The point is that at least you know you're doing something which is perturbatively meaningful in the loop expansion. There is the y with which you can go. But the y at which you need it is 4, and therefore it should have been nonsense. But everybody who has ever used it in some perspective, from some perspective or other, like Yakut and Orzag, or people who have followed up on that kind, do just a 1 loop leading 1 over y calculation and get very decent answers for the amplitude, which is a fortuitous thing because of the angular factors in the integrand, which actually suppress the higher loops very strongly. So that's just not something which can be quantified, but it is something which is real. Things work because the angular factors, the coming from the projection operators and the coupling constant, the m's which I wrote here. So they are important in this and helps one to get answers at low orders. So all right, so convergence of the perturbation series, I have no idea about, but the perturbation series exists at every order. The scaling solution is correct, and you can go ahead and also find the amplitude. So that's where that's about the D equal to 3 homogeneous thing. But now recently there was a result which was very interesting about the Batchelor spectrum for passive scalar. This is a result due to Bedrosian, Blumenthal, and Punchen-Smith. It's a mathematically rigorous proof of Batchelor's prediction about passive scalars advected in fluids with 1/k power spectrum. And what they did was essentially what we talked about, in the sense that they took a Navier-Stokes in D equal to 2 or a D equal to 3 hyperviscous, and they used a forcing which for Navier-Stokes was white in time and regular in space, and the scalar was subjected to white noise as well. So, all right, that prompts the in a way the next part of it, which is the stably stratified fluid, the Bolgiano-OBUKHOV scaling. Here the point is that there is a density gradient caused by a temperature gradient, a temperature difference of delta T over a length scale of D, and the additional feature is that the Navier-Stokes equation will have a buoyancy force. In the Boussinesq approximation, one can write it down in a very convenient form. The Boussinesq approximation means that incompressibility will be maintained, except when G, the acceleration to gravity, which is the big number over there, comes in. That G1, what you see over here, is hidden in the Richardson number. So there is this buoyancy force going in the additional bit, and then you have the advection of the theta, which is the temperature fluctuation. The energy, now comes the conservation law. The conservation law is for the energy which is now to be defined as the kinetic energy plus the Richardson number. The Richardson number is a product of expansion coefficient, temperature difference delta T, G, and some factor of D, the separation. And you look at this, you take this energy expression, you take a time derivative, and everything cancels out, and you have that is all the terms which are there in the equation of motion, except the dissipative part and the forcing part, they remain. So here in the first term on this right hand side, you see the dissipation caused by the viscosity, the dissipation caused by the temperature fluctuation, and then you have the forcing, which so if it's a stably stratified fluid, everything is working the Kolmogorov way. The first term as at small k and has the first term at large K and is dissipative, the second term at small k and is the input, and there is going to be total energy conserved. This is equal to the two are equal, the rate at which you are forcing in, and so there is again a tight transfer from one scale to another. And now there is a new situation. The kinetic energy spectrum, the spectrum that you are looking at is always the kinetic energy spectrum. And what we looked at before, the kinetic energy spectrum was dominated by, there was nothing else to talk about. The kinetic energy flow from small wave numbers to large wave numbers. Here there can be a new situation. The Richardson number part of the energy, the derivative of that at a particular k for large Richardson number may dominate the derivative, dominate the corresponding term coming from the kinetic energy. So you can have a new situation. The kinetic energy spectrum is dominated by a thermal energy flow, which we are calling it a thermal because it has the Richardson number, which is to delta T. So a thermal energy flow dominating things, that is things so far as the flow goes from low wave numbers to high wave numbers. And if this is completely dominant, that is what one calls what is the Bolgiano-OBUKHOV limit. So what you do is, once again, you the spectrum is obviously by the kinetic energy business. The total energy, on the other hand, which is this capital E of the Greek variety, is now this, and you take the derivative, and it is the second term, the Bolgiano limit, is drop the kinetic energy flux and assume as before that the transfer is K independent. The dynamics of the velocity field is consequently slave to the temperature in this Bolgiano limit. The velocity field does not have an independent dynamics. The dynamics is purely in the temperature fluctuation, and the velocity gets tagged to that. So this is what determines now the dimension. So I want to do a Kolmogorov argument. So how would I do it? What determines the dimension? So question is, what is the dimension of the temperature? The dimension of the temperature is determined by its tagging, it being slave to the velocity. The U dot is the thermal fluctuation. Therefore, it is the acceleration dimension, which is L over T squared. The energy transfer now has the dimension L squared over T5, and you do a dimensional analysis a la Kolmogorov, and you find K to the power minus 11 by 5. Universal spectrum, once again in this limit, and a universal prefactor. So what I would have for this limit is a scalar model. So scalar model in the sense that the velocity equation is actually just a linear equation slave to the theta variable. So U is tied to the theta, which is the temperature fluctuation, and the temperature fluctuation has a noise part in it, and that is the nonlinear transport of temperature, the advective transport over there. The transfer integral is now just coming out of this term over here. So it is theta theta dot, and so it is theta times this. So it is the 3-point function coming consisting of 2 thetas and 1 p. That is the transfer integral, and that is what you want independent of p. That gives you a constraint on what the h of k and t is exactly the de Dominicis Martin form. 1 over k to the power, it is a noise randomly stirred, but random stirring now in the theta field, and has the same characteristic as the of the de Dominicis Martin thing. So, well, the transfer integral is this, and now you do
sorry to interrupt you. You have 4 minutes left.
Yeah, right, sure. I'm all at the second last slide. So the scalar model with can also be written down in a wave number frequency space. So this is what you have over there. In time, which is what we saw in the previous. This is just a rehash of it. The correlation, as I said, is hk omega, which is exactly as the de Dominicis Martin setup. The transfer integral and the self-consistency of the one loop is assured now for z equal to 2 by 5 and y equal to 4. The thermal energy spectrum goes as k to the power minus 7 by 5. The thermal energy spectrum is defined by this line over here, the correlation of theta square and related to them. The kinetic energy spectrum, since z is equal to 2 by 5, and you have the tie-up between the kinetic and the thermal energy, the velocity and the thermal fluctuation, that carries a factor of time, which scales as 2 by 5, and therefore the minus 7 by 5 for E theta becomes the kinetic energy Bolgiano-OBUKHOV of 11 by 5. So you have but then the final issue that what is, I mean, you would never have in a finite Richardson number, what are you going to see? That why it is what we have focused entirely on two different limits. Richardson equal to 0, Richardson much bigger than 1, where, I mean, Richardson is completely dominant, and the other where Richardson is 0. The passage from one to the other can be accomplished by exploiting a trick. Heisenberg Chandrasekhar had a way of studying the crossover from Kolmogorov to the dissipative range. So the transition from k to the power minus 5/3 to a k to the power minus something which is appropriate to the large k limit. They had used a technique for doing this crossover, which one can borrow for this problem now to study a very different between two different kinds of turbulences going from Kolmogorov to this Bolgiano. And what does one find? What I find is that the energy spectrum, so you take an energy spectrum, fix a Richardson number, and take calculate energy spectrum. What you should find is that if the wave number is smaller than a particular wave number k1, the spectrum would be Kolmogorov-like. This wave number k1 scales as Richardson number to the -3/4. If on the other hand, the wave number is greater than a certain wave number k2, then E of k would scale as Richardson number to the -11/5. So the same spectrum, same E versus k would have a Kolmogorov part at the lower range, Bolgiano part in the upper range, and between k1 and k2 is Ri to the power -5/8, and between the k1 and k2, you would see a transition from the Kolmogorov to the Bolgiano. Over there, it would be some kind of an effective k-dependent exponent. So this is the crossover over here, and that's where I would like to stop. That here is where, at the end of the day, a problem which in this pure Bolgiano limit at least seems like a problem which is much simpler than the standard turbulence problem. And therefore, I mean, if one looks at this for multi-scaling and things like that, obviously, once again, there would be fluctuations in the constant transfer rate, and there would be exponents which are the higher order correlations would decay and would have a different k dependence as not really the what you would expect from the 2-point correlation, and therefore, but in the scalar field theory, it could be a much simpler problem to handle. So this limit is could be something interesting to look at. So thank you very much.
Thank you, Jayanta, for your talk. So are there questions? Now,
I put one in the box.
yes.
If I can ask. So Jayanta,
you can go it, Rahul.
okay. So Jayanta, in your way of handling this y basically as a parameter which sort of orders your loop expansion,
yeah,
where does the sweeping effect go?
Yeah, the sweeping, as I said, I mean, the sweeping comes from the question of the part of the integral, which is where the k is much greater. It is the infrared limit of the integral. So small p, which is problematic. Now, the point is, it is problematic only if I use the one loop with the Green's function and the correlation function as Lorentzian frequency dependencies, so that the frequency denominator is simply a minus I omega plus the relaxation rates. if that is what I'm going, if that is what my answer is in that approximation, the sweeping is, but a dressed loop would have a frequency convolution. So if an external frequency is omega, there would be a omega prime and a omega minus omega prime through the two lines that you have. And the sigma, the self energy, which has a low wave momentum, wave number divergence, would, when the wave number goes to zero, have a frequency divergence. The frequency and the wave number are related by a dynamic scaling argument, and that acts as a screener. So this convolution integral screens out this large P fluctuations. The P's have a contribution coming from the other leg, that is this the diagram with two lines, the line which is going at P equal to 0 and creating a divergence has a screening effect when I do the convolution integral with a general frequency, screening out that P going to 0 by bringing in a K minus P, which goes to K. So that I think that I thought was the way one is guaranteed that the Kolmogorov spectrum would come about without, from the loop integration, without having to be sort of derailed by the sweeping effect.
But this is something you can push through, or you just write the thing and you get a scaling form. I mean, is that it? Or you actually do the integrals?
You have to do the integrals. You have to first get a frequency, write a crossover between the K and the omega. Then you have to do the frequency integral to get the pole shifted and so on. But at the end of the day, you can write down what the final answer is.
Okay, I think there are other questions, so let's go. Yeah.
Yes, there is a comment from Mahendra Verma. I don't know if you...
For very large Richardson number, the flow becomes quasi 2D. Absolutely right. So I should have mentioned that I'm restricting myself to a Richardson number where I can still talk about isotropy without making big. So that's something which Abhik Basu and I looked at last year, that what is the range of wave number, what kind of wave number range and what kind of the Richardson number range would be relevant to sort of to make isotropic assumption work. I mean, so yes, right. But I mean, certainly at very large Richardson, it is a two-dimensional flow.
Okay. Are there other questions? Meanwhile, I have one. Is dimension playing a role in your calculations? Because in you know that
the dimension.
Numerics. Yes, please.
The dimension is playing a role only in that it is saying that energy transfer is the only transfer that I have. I mean, if I were to be in d equal to 2, for example, I would not be able to, I mean, there would be entropy to worry about, and this this scheme would fail. But if it is in d equal to 3 and above, then the conserved quantity is the energy. The moment you have more conserved quantities, you are you have to there's a problem. There will be a problem which you would have. As it stands now, only one conserved quantity, and therefore, so that which happens in d equal to 3 or absolutely. That's
okay. Other questions?
Sorry, if I can ask one more, Rahul Pandit here.
Sure.
Yes, please, Rahul.
You know, many people, including some people in the audience, like Itamar, have suggested using a quasi-Lagrangian representation for getting rid of the sweeping effect.
Yeah.
So is your scheme, I mean, in the end, everything should be equivalent. Do you think it will be equivalent?
Yes, yes. I guess I can't be absolutely sure, but what the quasi-Lagrangian does with actually keeping track of the flow is the same as the using a frequency-dependent frequency-dependent self-energy, which also is sort of trying to look at time evolution at various different scales. So essentially, I don't know how one can, but I do believe that at the end of the day, the quasi-Lagrangian way of getting rid of the sweeping should be the same as using a screening in a dress perturbation theory to get rid of it. The philosophy, I think, is to a certain extent similar. I mean, that it goes away because you are tracking the particle motion, and then you find that it is no longer there. Over here, you are tracking the propagator much more carefully. That's the way I would.
Okay, thank you.
Okay. So if there are no other questions, we thank again the speaker, Jayanta Bhattacharjee, and then maybe we have 2-3 minutes break.
Yes, I think we'll have a break.
And then we reconvene.
Okay, thank you.
So thanks a lot.